Hi everyone, welcome. So you all actually already know Brandon, and Chris already introduced him, and he said he wasn't going to introduce Brandon twice, but he did not say that Brandon was not going to get 2 introductions. So it is my tremendous pleasure to welcome Brandon here from all the way over in Wallace Hall. As you all know, Brandon is a assistant professor in the sociology department, and I'm so happy that he is my colleague. His office is 2 doors away from my office, and that is like a total blessing. Intellectually, that's a blessing because I've learned so much from him, and also just in terms of sort of psychologically. Like, we talk about stuff, I have a problem, I talk to Brandon about it, and he solves my problem, or he makes me feel better about having a problem. So anyway, it is, and I know this is going to be a great talk because this combines 2 things that Brandon is really expert in. So one is causal inference, and the other is text. And I think one of the things that Brandon's work does really well is make interesting combinations out of things. And so here we have 2 very large areas of methodology that are not that much in contact with each other yet. And Brandon is going to put them together, and I'm sure it's going to be in a way that is theoretically meaningful and precise and careful and useful. So Brandon.
Thank you so much. That's such a nice introduction. So hi again, everybody. So this is joint work with Naoki Agami, Christian Fong, Justin Grimmer, Molly Roberts, and then some of the applications I'll talk about we'll work with Dustin Tingley. This is a fairly new project in some ways, so I'm going to tell you about some things that we've been working on for a while, but the sort of frame of really thinking very seriously about what the causal, basically how can you make causal inference people happy with text analysis? That conversation is very new, and I kind of wanted to present something that was a little bit in progress, just because I thought it's, I don't know, a more interesting thing to do. So this is pretty early on, and I do really welcome your feedback. Let's jump in. Oh, actually, I was going to ask. So I know earlier lots of people had seen text analysis things before. How many people have seen causal inference in say the potential outcomes framework before? Okay, interesting. Okay, cool. Seems like maybe half the people. So we'll do a little bit of review. Okay. So I'm going to talk about 3 things. I'm going to talk about text as outcome. I'm going to talk about text as a treatment, and I'm going to talk about text as a confounder. A confounder, for people that don't know, it's something that affects both your treatment and your outcome, and it induces selection bias. And so it's like when we control for things in a regression, typically what we're trying to do is control for confounders. It's like, why are we doing it? And so we're going to talk about text's role in each of these places. Obviously, it could be in more than one. That's going to be really hard. We're just going to leave that for later. Okay. So, so the backdrop for this is that there's been a causal turn in social science at large. There's a lot of different fields that are undergoing causal revolutions, and they're happening at sort of slightly staggered times. And the attention to the methodology of causal inference is I think, driven by a need to sort of increase credibility. In fact, in economics, it's often called a credibility revolution. And it basically boils down to, we're just tired of these studies where one year it's oh, eggs are good, and then the next year it's no, just kidding, eggs are bad. And it's no, eggs are good, right? And it's because you can get lots of different answers with the same sort of data, depending on what you control for, how you set it up. That's still true, but the causal inference people are trying to really be clear about the rules and the goals and things of that nature. And so I would say this work usually does a few things. It tries to bring clarity about what the estimand is. So what is the thing that we are trying to estimate? And you would think that would be clear in every piece of work, but it very rarely is. And usually, establishing what we're trying to do is a hugely important part of doing it. It tries to separate identification from estimation. So identification tells us basically that with an infinite amount of data, we will be able to learn something about our estimand of interest. And then estimation is like how you actually go about like doing the job of taking the data and making an inference from it. And then it also places a clear emphasis on a counterfactual intervention. Right? The idea behind causal inference is what would have happened if we had done this instead of that. Okay? And so it's an intervention into the system and the difference between that and what we actually observe. There's two major frameworks for this. The potential outcomes framework, which is often called the Rubin causal model, and one based on directed acyclic graphs, which is associated with Judea Pearl. I'm going to talk primarily about the potential outcomes framework, but this sort of works in either school. And this is it's a multidisciplinary movement, which makes it a good place for computational social science to make some contributions. There's a lot of work in statistics, political science, economics, sociology, and computer science. It's all over the place. Okay, so that's the causal turn. Now, there's also, and this I don't have to sell quite as hard because this is what we're doing today, but there's like a current text analysis moment, right? That's coming from this astonishing avalanche of new data available and new methods that allow us to measure things we couldn't measure before. So, text analysis is becoming popular because these automated techniques, as I sort of said earlier today, improve reading. Right? And they complement human efforts. So if we think about interpreting a given sentence as analyzing a single straw of hay, this is something that humans are incredibly good at, right? Like analyzing English poetry is something you would absolutely want to give to a human because a computer is going to really struggle. But when you're comparing and classifying text, when you're trying to come up with these aggregate quantities, that's more like you're organizing or you're characterizing the haystack. And that's the kind of thing that humans are terrible at because they have very tiny active memories, right? And computers are able to make these systematic comparisons. So this is the kind of thing that you think actually would really be of interest to us, particularly as social scientists. And so we often think we're basically interested in characterizing and organizing the haystack. And what I'm going to sort of talk about today is ways of thinking about counterfactual interventions that go with this process. This is also an interdisciplinary movement with lots of other players with the digital humanities in particular getting in there, not so much on the causal turn with them. And there's also some nice connections to the hard sciences because a lot of the models, we didn't really talk about this earlier, but a lot of the text analysis models are isomorphic to models in like statistical genetics. So there's lots of fun connections there. Okay. So the computer scientists who work on the text analysis problems tend to think about exercises of prediction. And prediction is distinctly different from causal inference because there's no intervention, right? And so we need a lot less theory when we're doing predictive cases because we can always sort of hold out some data and check our accuracy. And so it's a very straightforward process. It's easy to know if we were right? We just predict and then we see what happens. Whereas with causal inference, what we're going to see is fundamentally we're never going to know we were right because it all turns on something we can never observe. And so in my experience, there's not like a ton of complicated theory to prediction. It's sort of about getting the sample and the population right. When things go awry, it's usually because you are learning your predictive model in a setting that is different than one where you want to predict. And that's basically what you guys are talking about tomorrow in framed in a different way. So we'll let that go till then. There's not a lot of work in this overlap space because it's primarily been pursued by two separate communities. Causal inference, by and large, takes the measurement strategy as given. Right? We just assume that the variables are there and we have them. And text analysis typically has not focused on the downstream social science inference because it's being primarily developed, by computer scientists and statisticians. And so I think there's really something to be gained in trying to bridge that gap. So with some areas of text analysis, this is all relatively straightforward, but things get really tricky when we start talking about unsupervised learning, which is what I sort of talked about earlier today and what we'll talk about here. So I just want to do one slide of causal inference background for those who haven't seen it, and maybe just a little refresher for those who have. So we're going to start by saying, suppose we have n units, right? So we have some number of, we can think of them as people. And every unit is going to receive a treatment, T sub I, right? That's the, T sub I is the treatment for unit I. We're also going to observe a response, Y sub I of T sub I. So that's the outcome for unit I when they receive treatment T sub I. All right, so we think about the treatment as maybe a drug or a placebo, and Y is whether or not you live or die. Then this is like whether or not you live or die, given that you got whatever assignment we plug in there. So the fundamental problem of causal inference is we don't get to see your outcome whether or like in both scenarios, right? We don't get to see your outcome under treatment and under control. And so we can't really calculate the counterfactual, which is what we care about. Like we want to know how much better off or worse off would you have been if we had given you this drug, but we're never actually going to get that. And so the quantity of interest that we end up being comfortable with, because, you know, to do anything else, this is like slightly too hard. In a simple case where the treatment is binary, might be the average treatment effect. And so that's the expectation of everybody when they got the drug or the treatment minus everybody's outcome when they didn't get the drug. And what's the linearity of expectations going to get us that's very cool is that we're going to be able to take the expectation of everybody when they got the drug, given that they were actually assigned to get the drug, minus the expectation of everybody under control when they got the control. So basically, we're going to be able to compare a control and treatment group, which is probably, you probably knew that's where that was going. So two key assumptions are going to make this work. SUPVA, which is going to come back later. It's the stable unit treatment value assumption. And basically what it means is that I can write y of 1, that I can write that down and like that has a consistent meaning. Basically that your outcome only depends on the treatment that was assigned to you, and that it's the same treatment that was assigned to everybody else. So there aren't like multiple versions of the treatment floating around, and like it doesn't matter that I got the drug, like whether or not I got the drug does not affect Chris's outcome, right? That's what's going on with SUPVA. And then the second is that there's no confounding. Basically, you can think about it very loosely as there's like no selection bias, right? It's not that people who are going to be healthier or perhaps, were more advantaged, right, have more money, took the drug. Well, that, as sort of, Gary was talking about the other day, right, like these particular, like, people and, like, the experiment in Mexico, like, some were, like, potentially able to, like, get the treatment even though they weren't assigned to have the treatment. That's obviously going to be correlated with certain amounts of resources that might also be connected to outcomes. Okay. And typically we get this no confounding by doing, like, random assignment of the treatment, because then we know the treatment's independent of, all the things. Any questions on this? I know that for people who haven't seen this before, that was probably really fast. I'll take a pause. Yes?
So the no confounding, is it specifically that Ti is independent of yi1 and yi0 for all I? Is that like the full written out?
Yeah, so if you have SUPVA, it's not gonna, like, you've already sort of assumed that the treatment index for other people doesn't affect.
I see.
And so, but yeah, and that, I guess that really should have little eyes.
Any particular given person that holds.
Yeah, that's right.
Okay.
That's right. Yeah.
The way you describe SUPVA, it sounds like you're talking about independence between observations. Is there more to it than that?
Yeah, so there's a few pieces. So there's no interference, which is kind of what you're thinking of, that like the treatment assignment for other people doesn't affect your outcomes.
Right.
The other thing is going to be that there's only one version of the treatment. That's not going to come up here, but you could imagine that in the drug case, maybe like different people take different amounts of the drug, right? And that's then, not quite the same. We also might end up recategorizing what the treatment is there and calling that a compliance problem, but that's not going to feature as heavily in this talk as the issue of, whether or not the potential outcomes are independent of other people's assignment. Okay, great. Okay, so I've sort of previewed this, but we're going to talk about 3 roles for text in the causal pipeline. Text is the outcome, which is that we assess a text-based response. I don't know why response is there twice. Apparently I'm very excited about it. And so a couple examples. I'm going to talk you through a case about an open-ended survey experiment where the outcome is, we're going to randomly prompt you with some treatment by exposing you, say, to a particular framing of a question, and then we're going to look at how that changes what you write. And so what you write is the text-based outcome. There's also some good work by Mike Gill and Andy Hall about the language that judges use where they're sort of using the randomization that comes from appellate judges being assigned cases and looks at just word use on like every word in the vocabulary. We might also think about text as treatment. So that is assessing the effect of text for you on something else, right? You're exposed to a text, and how does that change maybe some question you answer later? So we might think about this. Justin Grimmer's done some great work on this around advertising and messaging, and some work that I'll talk about in depth today is some work on discovering these treatments in text. And then finally, there's text as confounder. So we may not have the no confounding, but we might have no confounding within particular groups. And we might want to use those texts to define those groups. So basically, you can think about it as we're maybe going to try to find 2 texts that are very similar. One is treated and one is not. And we're going to use those to make comparisons. And so that's going to be, we're going to talk about matching with text in this particular paper. Okay, so causal inference with text at some points just looks kind of the same as it does in every other context. The randomization in the survey experiment is really what makes the wheels turn in the example I'm about to show you. Random assignment of appellate judges, like basically if you're randomly assigning the treatment, that's the thing that's giving you the most causal leverage. In the text matching case, we're going to make a common matching assumption of selection on observables. Basically, in many ways, the big pieces are the same. But there are practical and conceptual complications. So the practical ones are that these methods aren't always designed to deal with the high-dimensional nature of text, right? If you think about like a term document matrix, you can have a column space that's like, huge, and that's a little problematic for a lot of the methods that we typically rely on. Yes.
Sorry, I'm just having trouble following the example. I don't know these papers. They sound great, but what is the random? Can you give us just an example of what's meant by a random assignment there?
Yeah. So so in this paper in particular, they're interested in the causal effect of a female judge being assigned to a case.
So like how the language of her judgment looks different? Or
yeah.
Okay.
Yeah. And so nominally and lawyers in the room can contest this, but nominally the appellate judges are assigned randomly. Everyone I know that knows things about this says this is not actually true, but I do not know the details. But then you can then compare between the treatment and control groups because hypothetically it's been assigned randomly. Yeah. But the issue there is that you're getting the sort of differences along every individual word, which may or may not be what we care about. And so we're going to talk about like how do you think about differences along groups of words, and that's where the topics are going to come in. Yeah.
So that paper's looking at random assignment of a female judge on whose outcome?
On the text of the opinion. Okay. Great. And then we're also going to think about like, there's going to be some practical questions about just how we define our treatments and outcomes. I think the conceptual questions are going to be things like, well, if we're discovering a treatment, what does it mean that our treatment changes every time we do an experiment? It's kind of like bizarre. How do we think about talking about bias in these scenarios? There's also going to be questions about what are the quantities of interest, right? What is the implication of the outcome itself being a function of the treatment assignment? Not great is the answer, but we'll talk about that in a little bit. So some things for today. The implications of working with causal inference when an outcome, the treatment or the confounder is not known at the start of the study. We're going to talk about formalizing the process of discovery. So part of this is I'm going to make an argument to you that some of the issues I'm going to raise actually aren't new. They're just not really talked about because they're part of the process that we don't discuss typically when we talk about research. And there's going to be a connection to like an unformalized procedure, basically like when we come up with codings by hand, which is essentially how like lots of these survey experiments are done, we actually run into the same problem because we're actually doing the same thing. We're just not having the computer help us. So this is a new frontier, and lots of these things aren't going to have clean answers, so I just wanted to, put that out there in advance. This is the part that's like in progress. So let's just jump in with text as outcome. I'm basically going to give you a motivation and an application, and then I'm going to talk a little bit about how we think about this in a causal inference framework. So the example here is drawing mostly from this paper up here about topic models for open-ended survey response. And here's the core idea. So we're interested in how an intervention changes the content of what people write. And so we're thinking about changes on some function of the text rather than on each individual word or phrase, right? We could without too much problem, go in and evaluate the difference on every individual word. We'd have like a huge false discovery problem, but like we could solve that with some statistical corrections if we had enough data. But instead, actually, what we think when we think about this intuitively is something about the categories are changing, right? Like if I prompt you to be worried about something, we think you're going to talk about a set of concerns more that is going to be across a bunch of phrases jointly, right? And that's what we're going to talk about. So the structural topic model here is going to provide us with a low-dimensional summary of the text, and we're going to think about movement in terms of the topics. And it's nicely also going to explicitly model the covariate relationship for us. And this is going to come back to the question that came up earlier today about, like, isn't it a little wonky that it's doing those things at the same time? So in many areas of life, and this is just motivation for why we care about this in surveys, people communicate by writing or speaking, and yet most surveys are using these pre-established scales or categories. If you think back to Gary's talk yesterday, he sort of talked a little bit about like how survey questions are actually shockingly hard to write. It's shockingly hard to anticipate what it is that other people are going to say. Right? There's a sort of remarkable number of studies that ask people, why did you make this choice? And one of the options is none of the above, and that turns out to be like the most important and significant category, right? And that's just because it's like hard to anticipate why people do things. So there used to be a big debate about this, and there isn't as much anymore. Basically because it's just really hard, right? It's really hard to do open-ended surveys, particularly at scale. And most researchers then opt for closed-ended surveys. And so what this entails is choosing a number along some scale that a researcher has predefined, or ranking some set of categories that the user has defined, sometimes putting in other option. And so, again, there's some debate about whether or not this is a good idea, but sort of unarguably there's a workflow advantage, right? Like, in like 10 minutes, I can like put up an MTurk survey, get some replies, and then stick the data into Stata and like type regress, right? Like, there's like a very there's a cleanness to this, huh? Well, I mean, I'm kind of mocking this viewpoint, so I just throw Stata. You guys aren't going to do this. It's going to be great. So the distinct advantages then to open-ended questions, we don't cue respondents to think of particular causes. We don't force a particular dimensionality reduction. I mean, we're going to have one eventually, but we're going to learn it inductively. We're going to provide insight into the mechanisms that connect the treatment to the outcome, and arguably you're yielding the most salient response rather than the one you guessed in advance that was the best approximation to it. There's some disadvantages. It's very expensive to do, but part of why we wanted to argue for the inclusion of topic models is it makes this stuff a lot easier and more tractable, particularly when you have like enormous numbers of text. Okay, so in the paper we give an application to 2 experiments and some work on the American National Election Survey. I'm going to show you one of these examples that comes from Alberts and Guderian. This data actually is in the R package, so you can, the STM package, so you can just play around with it. It's in an object called Guderian. And so that's a fun option if you want to see how this works in like survey sense. And what they're interested in is the way that fear and anxiety leads to searching for information about threats. You can see this is like a shockingly prescient article, although I think they ran these analyses in 2013. We also have an example on spontaneous giving and calculated greed, and then we do some stuff with the ANES, but like I said, I'm going to focus on this first one. So the treatment condition is going to be some stuff, and then when you think about immigration, what makes you worried? Compared to when you think about immigration, what do you think of? And so the only difference is going to be in the way that we frame this question. Do we frame it as what do you worry about? Do we frame it as what you think about? That's the randomly assigned intervention. So the argument is that basically if we nudge people towards worrying, does that change the way they express themselves about immigration? And in the original analysis, they used some pre-established coding categories based on fear, anger, and enthusiasm. And they showed that the treatment had an impact on fear and anger. So some example texts, we estimate a topic model. I think we estimate a topic model with 3 topics to sort of mirror their original 3 categories. I think if I was doing this now, this was like one of the first projects we did, I think I would do it with many more topics. At the time, I think we thought it was going to have trouble scaling up in that way because we had very few documents here, so for what that's worth. But you get some things like this. So problems caused by the influx of illegal immigrants who are crowding our schools and hospitals, lowering the level of education and the quality of care in hospitals. And topic 2 is going to be, a bit more tolerant, right? I worry about the Republican Party doing something very stupid. This country was built on immigration. To deny anyone access to citizenship is unconstitutional, right? You can see this like a much more like open perspective towards immigrants than up here, where there's sort of mostly a concern about crime and like other issues. And in fact, what we find in an effect that's somewhat moderated by party identification, the treatment sort of dramatically increases this use of topic 1. So this here is the topic proportions. That we're seeing that when we tell people, we ask them what they worry about, they give us concerns that deal more with crime. Now, that's sort of an interesting study. You read Guderian and Albertson's paper, and they now have a book that goes through a lot of these things. It's great. You should read it. But now let's just talk about methodologically what we think about that from a causal inference perspective. Because I think there is a sense in which, like, mechanically, that's just a useful way to think about surveys, right? So in a traditional survey experiment, we're relying on the randomization of the treatment to give us ignorability, or the no confounders assumption, right? We know because we randomize the treatment, we know that there isn't something that's both associated with the treatment and with the outcome that is, pre-treatment, because we've randomized the treatment. So the fact that the subjects don't know each other, they're on this like survey platform, and the fact that we are like, we don't even have we don't even have someone asking the questions, right? It's just like what shows up on your screen. We can be pretty confident that SUPA holds, right? There's probably not interference amongst the subjects because they're like mechanical Turkers or people we got in a Qualtrics panel. We can also be pretty confident that there's like one version of the treatment, depending on how we carefully define what the treatment is, which is basically exposure to this word. But the argument that we're going to make in this paper, when we get it written, is that actually there's a very subtle, particular type of SUPA violation that's going on here that we call analyst-induced SUPA. Okay? And that is that when we discover an outcome, when we discover a function of the text, we've now induced a situation in which the learned representation of the text is dependent on the particular randomization we got. right? Because
When you say, sorry to keep it,
No.
when you say text, do you mean this text of the survey experiment or the
The-
writing that people are doing?
the writing that people are doing.
Okay.
So the open-ended response they give. Yeah, thank you. That's
Oh no, sorry, that should be the open.
Yeah.
Okay,
Yeah.
It's the function of the text.
And so the issue here is going to be that subtly, right? It is that someone else's treatment assignment affects your outcome. And why is that? Well, because their treatment assignment affected what they wrote. And what they wrote affected what we learned in the topic model. And so that topic representation is affecting how how we code your particular document. So if we imagine rerunning the world again, but this time Chris doesn't get the treatment, that still could affect the way we code my document. And from a causal inference perspective, we find that deeply unsettling.
Just to make sure I understand,
Yeah.
this is assuming that you do the topic model after all of the text or survey answers have been written.
Correct.
And so maybe, I don't know if you're going here, but if you had done it beforehand on some pretext, that
Yep.
would solve this problem? Is that?
Yep, that's where we're going. Train test splits. Answer to so many things in the world. So we can think about this problem as informally related to overfitting, or what Andrew Gelman calls the garden of forking paths. Which is, the reason I sort of bring this up is that I think these issues are actually quite subtle, but we need to be attentive to subtle issues because it's very easy to be sort of unconsciously biased by things. And so you really want to set up the norms in a discipline in a way that there's not this capacity to sort of drift into overfitting. We haven't been great about that in the social sciences, but we try. Okay. So in this text as outcome setting, we observe the treatment directly, but not the outcome y. The y is instead a function of the observed words, and we're going to denote it like this. So yi, the thing we care about, is equal to g, some function that we are learning, of wi, which is the words in your document. So what the topic model is doing for us is learning this g function that's projecting from this high dimensional space wi into a lower dimensional space y sub I. So the SUFA implies that these potential outcomes are invariant across treatment assignments, but as I just explained, they're sort of not going to be. And so the concern we have is that this g function that we learn is dependent on all the treatment assignments, and hence analyst-induced SUFA. So the argument that we make, though, is that this isn't actually specific to unsupervised methods at all. In fact, we can cast any kind of hand coding rule as a g function, right? It just happens to be one that's, carried out by undergraduates that maybe we pay with pizza, right? But they are still a g function, right? They are taking a text and they are mapping it into something else. And so if we go through the text and use it to develop the codebook or refine the codebook in some way or change the coding rules, we run the same risk of this analyst-induced SUFA. Okay. So the solution, as was sort of reviewed very nicely, is we just need to do this on a different set of data. Now, sometimes you just have floating around a nice set of data that you could learn the model on, but often the answer here is going to be a train test split, which is that this is very common in industry under the name A/B tests. It's very common in machine learning under the name train test splits. And we can think about, well, first let me say, okay, so there's two ways around this. There's not just train test splits. We can assume stability in the topics across randomizations. We can basically assume that because there isn't that much variation in what people would write under training and test, that the topic model would give us the same structure every time. This is, I think a questionable assumption, but maybe something we could empirically evaluate. Okay, the other option is this train test split. And what it's going to let us do is it's going to let us take a set of documents that we're going to call our training set, and we can do whatever we want to this set of documents. It's going to be great, right? We can do all the things that might be called data mining in a bad sense. We can look around, we can figure out whatever we want to do to discover the function of interest, and then apply it to the test set and be confident that we're still going to get a good estimate of the causal effect. Because we're not evaluating on the same model where we're finding this g function. And so it becomes just like any other measure. And so, and crucially, we don't have to assume that this is the true or correct G function. We don't even have to believe that there is a true G function, because we are essentially conditioning on the existence of this thing, which puts a lot of pressure on the way that we choose to label this G function, the way that we choose to talk about it, right? We say, this is a topic about crime, right? Well, that has to be an accurate label. But that's the same problem we end up with topic models all the time, right? That's a problem that's solved by validation, by going through and, making sure these things correspond to the labels we give them in a, systematic and regular way. So, so that's text as outcome. Yep.
And just back to like the first option of assuming stability.
Yeah.
Are there any conditions under which that would be a good assumption? Like, does it depend on the number, the sample size at all?
Yeah. So the sad thing is that I would believe this more I would believe it more under a fixed randomization scheme where we have a certain number of trained and treatment and control units. So like we're always going to have the same number regardless of how we randomize. And I would believe it in a setting where the document size was really, really, really big, right? And the problem is if it's really, really, really big, you can like just do a train test split and it's like less of a problem. So the downside of this, right, is that it takes you take a real efficiency hit, right? Like you're losing like probably half of your documents, and that's rough. And one of the things that we're evaluating now is trying to get a sense of like, how do you assess the stability of models under these different train test splits? And like, what can we do to promote more stability amongst train test splits? Because you would like to believe that like the thing that you find isn't going to be a function of how you happen to split your data. In some sense, it's okay if it is, but like it still would like unsettle us a little bit. So my intuition, and I could just be totally wrong, right, is that the bias from this is not often very large, but it definitely like this is what you need to do to like make this work in the classical causal inference framework. And whether or not that's the standard we want to hold is a different question entirely, but we wanted to see like what were the issues, like how could we frame this problem? Okay. Yeah.
So it's basically speculation that this is empirically not a big problem. I mean, you could possibly, get some data, train it in the wrong way, then do it the correct way and see what the difference is, right?
You could. So the difficulty is, and this is where causal inference is just hard, right? You never observe the counterfactual, right? You only get the one potential outcome. So you could say, do this process a ton of times and look at differences in the estimates of the average treatment effect. But even then, like sample variation would make it really hard. The G function is moving around in all of these different cases, and so it's not measuring quite the same thing. And so I think it's actually kind of shockingly difficult to determine whether or not, like to know what the right comparison is, which is, a huge complication, right? And is a difficult reason you probably actually just don't want to make this assumption if you can avoid it, because it's, we're going to have a hard time substantiating it. Great question. Yeah?
I'm failing to understand the intuition behind why you're violating the SIPA if you just ignore the control and treatment assignments and train a topic model on all the things.
Yeah. So, okay, so let's speculate we're in a world where the treatment does something. Okay? This is not a problem in the world where the treatment effect is exactly 0, but if you're in that world, like, you're not doing an experiment, right? Like, why would you if you believe that was true, right? So, so if I get assigned a treatment, then I'm going to write about something different than if I had been assigned control. And what I choose to write about is going to affect the model, which is then going to affect the representation of what you, how we code your document. So let's just let's think about like a really extreme example of this. Let's say we're all in this room in this experiment, and when treated, I asked you to write about statistics, and when control asks you to write about data science, okay? If all of us were assigned control, we would write very different things, and the topic model would learn different topics than if we were all assigned treatment. But what the sort of causal inference framework demands is that actually the outcome we have is invariant to those different treatment assignments. That we need to know that had we assigned you treatment, we would have given you the same response regardless of whether or not I was assigned treatment. Yeah.
Oh, does bootstrapping come into play with the tests? I don't really get how it works, but it has to do with the training and the test set?
Yeah, so basically what's going to happen here is in the training set, it's basically just like another set of data that we happen to know is drawn from the same distribution as our original data, which means that we can learn this G function without worrying at all about, it messing up our estimation, basically, of our ultimate causal effect. And so we just do whatever we want in the training set, and then in the test set, it is though we have come to it with a new with a new measure that like we didn't discover, right? It's like we came to it with some given to us from above measure, because it does not depend on the documents where we're trying to estimate the causal effect.
But what is like the bootstrapping with replacement and all that stuff?
Yeah, so in that context, that won't help us here. So that's a way of bootstrapping is like a way of estimating variances of things, and that won't help us here because we would still end up drawing in units that were connected to our other units. Yeah.
So does this also apply to situations in which we're being more primitive about the way we're coming up with a G function, like you mentioned, hand coding?
Yeah.
So for instance, if I have 80 interviews that I'm coding by hand, if I were to queue properly to a causal inference framework, does this suggest that I should code 10 of them by hand and then come up with topics and then apply those topics to the remaining 70 or something? Is
Yeah.
it that far-reaching?
Yes.
Yeah.
I think there's an open question about whether or not I would advocate you doing that.
Right.
But to make the math work, absolutely.
Yeah.
Yeah.
So I don't mean to be a pain, but
No.
in terms of intuition, so I understand sort of the causal inference approach to using experiments with text as the outcome, but if that's not what you're doing, then what problem are we trying to solve with this new method? Like what causal, like why not just do an experiment and just have text as the outcome? Like what is the causal inference question?
Oh, so the causal inference question is if I change, say whether or not I prompt you to be worried or not, how does it change the topics you write about?
Right, I get that.
And so the issue is, ex ante, I don't know what are the types of topics you're going to write about. And so what I'm going to do is run the experiment on everybody, then take like half the room and learn what kind of topics are actually used, come up with labels for them, et cetera, learn a set of parameters, and then on the other half of the room, just fit into those existing topics without updating them, and then calculate my causal effects.
Okay.
So someone else go on. I've been talking too much.
So, I think that the reason why this is hard for me to kind of connect to intuitively is because, so I understand, if I understand correctly, this only applies to the problem of discovery inductively of labels. If you create a labeling scheme before you ever run the experiment, this is not a problem.
That's
Am I
right.
correct in that?
Yes.
Okay, so
You potentially have a different problem that it doesn't map onto anything that you intended to, but yeah.
yeah, but this is only like when we were doing topic modeling and discovering this scheme afterwards, and so I kind of understand the problem of overfitting data. That's why we hold out data from supervised learning.
Right.
But in a discovery, how common is it to come up with one topic model without ever using your kind of hermeneutic capacity for interpretation based on your own priors, and then picking the one that like this seems to assume that there's that you run a topic model, just get whatever comes back to you, without actually the process of interpreting those based on what you think the research question is.
Oh, no. There's still all of that. You do all of that in the train set.
Mm-hmm.
So you find the topic model that captures the thing that you want to capture. You do all the labeling. You think about it. You make sure it's the measurement instrument that you want. But then instead of using those same documents to estimate the quantity, you say, well, now I have this measurement instrument, and I'm going to apply it over here on this like virgin set of documents we haven't touched yet.
Isn't there like maybe I'll think about articulating my question a little bit better.
Yeah.
Isn't that sort of, so you have unsupervised learning applied to one set, and then it becomes supervised in a sense for the other?
Yeah. No, that's exactly it. We're basically using the unsupervised learning to learn what will become a supervised representation. It's just that like we're going to inductively discover the categories. But you're right. In terms of what's going on in the test set, it's basically like it's the same as applying a supervised learner. It's just that you trained it in a different way than you typically train supervised learners. Yeah.
So you mentioned efficiency briefly, right? There's a reason people don't usually do two-fold cross-validation, right? It's like you're wasting a lot of data. So is it possible to do like a k-fold and then just figure out your treatment effect and confidence interval as an average across all the folds?
So the issue is the G is different in every fold. And so you can't average them because they're different things. You're like averaging different. It'd be like if I, in one set, measured GDP and another set measured, something else, trade flows or something, and then like average them all together. Like it wouldn't quite work.
But we don't have any particular interest in the G itself, just how it affects our estimate of the treatment, right?
Right. Well, how the treatment estimate affects its outcome, right? I mean, we care about the G insofar as like it is the thing we're measuring, right? It is the outcome that we care about. Okay, let me go to textures treatment, which has a different set of concerns, and we can like circle back here later in the talk. This is good though. Thank you guys. Okay, so this work is a lot of it was done by Christian Fung and Justin Grimmer in a piece for ACL. Molly Roberts and I are working with them on some follow-up work, but I do just want to clearly, like, again, we're sort of weaving all of these things together, which is why I'm giving it in the talk. But I, want to be very clear that this is a lot of the great ideas here, really, with Christian and Justin. So here's the running example. Let's say that we're thinking about how voters evaluate candidates. So candidates have policy positions, they have partisan affiliation, which is what we typically think about, but they also have lives that they live before, they have elected office. And so we might think about what biographical facts about somebody's life affects the voter's evaluation of the particular candidate. And so we could run a survey experiment, right, in which we show people like two different bios, and we have them rate one or the other. But the problem is there's like a lot going on in these two bios, and so it wouldn't exactly be clear what are the features that are salient here, right? There's like a whole mess of things going on in any two bios. And so we're worried about like generalizing what features would drive any differences we observe. Maybe we find that this person is liked a great deal more than this person, but I'm not sure that has taught us anything about social science yet. Okay, so a second thing we can do is we can directly manipulate a piece of text in a particular way, right? So this is really classically how this is done in a text-based survey experiment, okay? So you have some bios, so this person majored in economics, political science, and blah, 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 blah. And then you change the signal that is given in the people that you mentioned in the writings, right? So you've changed a sort of signal about like, your political leanings here quite a bit, okay? And so to do this though, it successfully isolates the feature of the text that's going to drive the response. But the problem is you have to know it in advance, right? You have to be saying, oh, I'm going to manipulate this particular thing, and we have to know that's like what we want to manipulate. Okay. So the question we're going to ask is essentially, can we invert this current approach and find the interesting treatments that would have to be known in advance under this other scheme? And we want things that are going to occur frequently in the population of text, right? We want it to be like not something so idiosyncratic we can't effectively measure it or that no one will care. And we want it to have a large effect on individuals' decisions, right? Because, I don't know, we're in the business of big treatment effects, right? We'll like those. They give us stars. There's one thing you should learn from this workshop. It's all about stars. Good. Glad people laughed at that. It would be depressing if they didn't. Okay, so we're going to invert the current approach, and we're going to take a population of texts, and we're going to discover the treatments. And so we're going to do this while simultaneously trying to estimate the marginal effects of those treatments. And there's like a spoiler alert, right? Again, we're going to sort of come back to a train test split. That's what's going to make a lot of this machinery run. Okay. So first, though, we're going to identify a particular estimand. So we talked about how causal inference is very good at being clear about what the estimand is. In the previous case, it was the average treatment effect. Because there was like a single treatment we were moving. Here, there's going to be like a lot of things going on in a given text. There's actually going to be a lot of treatments. And so we're going to need to figure out how we define an effect. We're going to do something called the AMCE, the average marginal component effect. So essentially what it's going to do is it's going to isolate the effect of one treatment, holding all the other treatments constant. So there's going to be 3 steps that's going to make this work go. We'll prove that the interventions at the text level identify the marginal effects of the underlying treatments. So basically, this is an estimand that can be identified. We're going to have a method for discovering different features. In other words, we're going to have a method for discovering treatments. And we're going to have a method for estimating the marginal effect for discovered treatments. So basically, we're going to find what these treatments are in the text, and we're going to do this estimation. Okay. All right. So yeah.
So this is like a conjoint survey experiment, but
Yeah.
without running the conjoint survey experiment.
Yeah.
Like the estimand is the same.
Yeah. You can think about this as like a conjoint where we discover the features that are being manipulated in the conjoint. Yeah.
So you're saying that in all the causal inference papers, the randomization is providing the causal leverage.
Yes.
And so it seems like the place where there could be, like the most controversial thing seems like it's going to be number 2, where you will presumably, quote unquote, discover randomization in this text.
So we're going to actually randomize who sees the different bios. And then we're going to need an assumption that's going to help us bridge from that randomization to the randomization of the treatments, which I'll show you in a minute.
Okay. Well, so is this basically an experimental design then, or is it a way of?
It is, yeah.
All right. All
Yeah.
right.
But it's an experimental design insofar as what we're going to do is randomly assign different texts to people to read and have them rate the text. And that's going to randomize the treatments, but it's going to randomize them as blocks. And that's problematic because they're sort of naturally occurring blocks. And so we're going to need an assumption to be able to deal with that.
Okay.
And what you're going to see is that there's going to be things here that are similar to the text as outcome case, but there's like certain pieces that are very hard in text as outcome that become really easy here, like the outcome is fixed. And there's going to be other parts that are much harder here. All right. So, so the individual is going to see a text. This is some xi, and we're going to infer some treatment in the text. So here's this g function again. So the idea is there's some mapping between the actual words in the text and some lower dimensional set of features. Things we could think about as like signaling things about the candidate. So the things we're going to have to assume is that there's no spillover, right? So the assignment, your rating of a candidate is not dependent on somebody else's, the text that was assigned to somebody else. Okay, that's like not too hard. We're going to need random assignment of the text to individuals, also not too hard. And here's where the work is going to come in. So we're going to need an assumption of sufficiency, which is essentially that for all texts, and for all x and x prime, so basically 2 pairs of text such that the G functions are the same, so the representation they produce is the same. The expectations of the outcomes of the ratings have to be equal. And that's what's going to allow us to bridge from the randomization over to like learning things about the individual treatment effects. Yeah?
Could you give a concrete example of where two different texts, x and x prime, would have the same z? Same
Yes.
Z of x?
So let's say one of the features we're going to end up learning in this particular example is the person's a lawyer. Okay? There's a bunch of different ways to signal a person is a lawyer. And so we could write that with like all kinds of different word counts, right? Like there's like, you know, could say, I don't know, lawyer's weird because the word lawyer always shows up, but there's like lots of things. You could talk about the law school they went to, you could talk about like particular law schools, you could talk about their practice as a lawyer, like all these different things. And what we need it to be is for any pair of those representations where they both end up having the same feature that they are a lawyer, we need it to be that the expectation of the rating is constant. And we also are going to need common support, basically that all combinations of features have non-zero probability. You can get around this, it just changes the estimand and makes it a little bit hairy, so it's easier to talk about it where all combinations can pop up. And it's going to turn out that one can prove that these assumptions are sufficient to identify the AMC for some arbitrary k. So let's talk about how the discovery works. The basic process here, we're going to randomly assign the text. We're going to obtain some responses. So like I'm asking people to say rate people. We're going to randomly divide text and responses into training and test sets. This is going to avoid the technical issues with using the entire sample. So we're going to basically bypass the analyst-induced SUPA problem again. And it's going to deal with like the false discovery problem, right? It's going to allow us to explicitly search in the training set for treatments that will have a big effect on the outcome without like biasing our estimate of those treatment effects. So, okay, so we're going to use both the documents and the responses to discover this mapping. Because again, we don't just want things that explain what's going on in the text, we want things that also explain the rating. A logical choice for this would be something called supervised LDA, which was in that giant list of LDA models I showed you. But basically the idea here is it learns a set of topics that are predictive of some piece of metadata. And so one could imagine the logical thing to do here would be to find a set of topics that were predictive of the outcome. But what turns out to be interesting is that whereas that representation of the mixed membership model is really convenient for the text as outcome, it's going to be impossible to work with as a treatment. And because it's going to imply that marginalization is impossible. Right, which is basically to say that if the representation is your some proportion in each of various topics, I cannot raise your proportion in one topic without decreasing it in some others, because it has to sum to 1. So what we're going to do instead is use a different type of model called the supervised Indian buffet process. I'm not going to go deeply into this, but the basic idea is instead of having a mixed membership representation, it's going to have a representation of a series of binary features that can be either on or off. Okay, so you can be a lawyer and also have military service, or just be a lawyer but not have military service, or just military service but no lawyer. Like you can do whatever combination of these binary things. And this is going to be a sort of natural way of representing that.
Do you know why it's called that?
Yes, there is a famous stochastic process called the Chinese restaurant process that is named because there's a little cute story that goes with it, but I can tell you later, that has to do with apparently, I have not been, giant round tables that are in San Francisco Chinese restaurants, and this, where it's being developed at Berkeley. And so once that name stuck, because it goes with the metaphor really cutely, other people that were developing non-parametric processes started coming up with really cute, like, other things. And so the idea here, the story, and it's kind of like, you know, when people choose acronyms because they spell a word, and then you go back and you figure out like how you can make the acronym work so it spells that word. It's kind of like that, but the way they go back and justify it is that you're sort of walking by a buffet and you either take an item or you don't take an item, and you can take any sort of combination of items as you walk along. Okay. Okay, so the full procedure then is we're going to divide our text up. We're going to do the training set. We're going to discover the mapping from the text to treatment using the model I just showed you. And then in the test set, we're going to infer the treatments and measure their effects. Yeah.
Does STM have the same simplex assumptions? And have you thought about replicating this paper up with the STM model?
Right. So STM has a representation that is on the simplex. So it's a proportion in each topic. And so it wouldn't work. What I would like to do at some point, and it's just a matter of having the bandwidth, is basically take this and like develop an STM-like package that can run all of this stuff. But STM took me a while, so who knows.
So in terms of the application, like under what circumstances would researchers have the text but not know the treatment? Or like if we put in, say, a survey experiment, I guess you would have some wording of some questions, but you don't really know what these different wordings are measuring. Right. Is it like,
yeah, you probably wouldn't write the wording as much as there would be texts that are out there. So for example, let's say that you took, so for example, one of the things that I'm not talking about here, you've taken a bunch of complaint data from the Consumer Financial Protection Bureau and look at how long it takes you to get a response to your complaint. And so there are probably some features of the way these complaints are written or what they're about that affects the wait time you get in the response. And what the procedure does is essentially learns what those things are and then estimates their effects.
So it's almost like so put it in survey experiment context, it's like circumstances where you have the measurement but don't know the construct behind it. And this is inferring what these so-called measurements are measuring, like
yeah, you could frame it that way. Yeah, right. The text is the measurement, but you don't quite know what's doing the work in the text. So you could use a combination of things. Yep. Cool. So here's an example of how this works. You have, say, a nice little bio. You take out the person's name and replace it with a fake name, so we're not getting associations with particular people. Each respondent is going to see 3 texts from a corpus of around 2,200 biographies. They're going to observe the text, and then they're going to rate them on a feeling thermometer from 0 to 100, how much they like this person. There's 1,800 participants and 5,300 responses. Okay. We're going to split these into half training, half test. And so here's what you find. Right, so here are the treatments that have big effects, and we find some things that like sort of intuitively make sense. Right, people in general, you can see treatment 10 here is sort of about military service. People like that. People don't like lawyers, right? And so there's a nice little negative effect there for feature 9. So it's good. If we found that people really loved lawyers, that would probably be worrying. People like academics, right? Director university received president PhD policy. It's nice here and positive, so we can all feel good about that. And obviously, it confirms my prior that people like me, so I believe it, and it's great. Yeah.
Do these, in your model, does it assume that these treatments have homogeneous effects?
No. No, and in fact, you can have effects that are different, like you don't even have to assume that the effects don't interact with each other.
Right, yeah, that's kind of what I'm getting at.
Yeah, no, because you're marginalizing over them,
Yeah.
and so the question becomes, what do you marginalize over with respect to? And that's the part that I kind of glazed over.
Yeah.
That's a big thing in conjoints as well.
It's just hard for me to believe, like, I like cheap things, and I might like tattoos, but I might not like cheap tattoos.
Sure.
So having those two things in the same text, right? It's like so contextual.
Yeah, absolutely. And in this context, maybe that wouldn't give you a great perspective, right? Because of what is actually going on. Hopefully, you would get like one feature that would get the combination of those things, but you might not. and then you would still get a properly defined S demand on cheap, but it might not be the actual treatment effect you care about. And that of course is the crux of a lot of this stuff, is that like part of the issue of discovery is you're trying to discover a thing you care about, and there's no guarantee that the model is going to give you something that you care about. But what's great is that these are tools that you can use to like root around without worry that you're going to mess up your experiment to find the thing you care about.
Do you, the researcher, specify how many treatments there are?
Yes, in this context, we can also learn it. That's part of the nice thing about the inning buffet process is it learns the number of features. Okay.
I just wanted to make sure I understand the estimation process here. Now that you've got your features, you've got your 10 features. Are these each dichotomous?
Yes.
These the Indian buffet, and these are what, just regression coefficients here, or? Yeah.
So the things, the sort of confidence intervals here are coming from like a bootstrap procedure, but basically, yeah, you're projecting what the features are in the test set, and then it's just like we happen to observe those, and so you can analyze it just like you do a contract at that point.
Have you validated it the other way around? Like take a text and add a feature, see if it actually produces the rating that you expect it to?
No, that's really interesting though. I mean, I think one of the challenges that's very difficult about this in the text as outcome case, and this is just a thing about text analysis, it's profoundly difficult to generate realistic text. And it makes it really hard to do simulation experiments where at some point you have to generate a text. But I think that's it's a really interesting idea. We've applied it to a bunch of different contexts, and you get like very nice intuitive results that are like stable when you like do it again. But I think that's a great suggestion. Okay. Oh yeah.
I assume there's no IV version of this.
Right. So I think at some point, I think text as IV might be an interesting thing to do. I think the exclusion restriction in IV is already almost never satisfied. I'm a kind of like IV skeptic, and so I can't even imagine how much harder it would be in this context. So there's a great paper that gives me a sense of why I think this would be very difficult by John Marshall about coarsening bias in IVs. And basically what he shows is that in settings where, let's say you have a treatment that's continuous, but you dichotomize it for the IV because it makes life easier. So it's like, say, years of schooling, and you dichotomize it to, did you finish high school or not? You actually induce a exclusion restriction violation that might not have been there otherwise. Because while the thing is in control, that the instrument is, like the uncoarsened version of the treatment, it's ticking up as a consequence of the instrument. And it's also like affecting the outcome, but it's not getting captured in the actual treatment. And so it's as though it's basically like, it's creating a path that, I can draw the DAG for you, I can do it later, but basically it's inducing an exclusion restriction violation that wasn't there, and it comes because of the way you measure the treatment. That makes me very nervous that trying to do this in an IV setting would be very open to those kinds of problems. But I gotta think about it a little bit.
The application I had in mind was just using IV to analyze experiments with compliance.
Right.
So the experimental variation would have, I assume, no exclusion restriction problem because it's random.
I see. So you're thinking about it as like the measure of compliance? Or what's the text doing in that context?
So the text would be, I have a particular application in mind.
Okay. Yeah, let's talk about it afterwards, yeah. Okay. So the challenges that are straightforward to address here, you can't marginalize over the simplex, and so we get this sort of alternative binary feature representation. Easy-ish problem to solve. We have concerns about overfitting, but that's fine. We have this like train test split. Some challenges that we're in the progress of fixing. So there's some strong assumptions about sufficiency. Justin and Christian found a very clever way to weaken the sufficiency assumption. I showed you the weaker version. It was stronger before. But we're also developing some empirical tests to evaluate that. There's some efficiency loss from the train test split again. but actually this is a much easier problem to solve. And the reason is because as soon as we take the outcome out, we can now estimate that model on the complete data set. And what that means is we can estimate the complete model on the data set, the model on the entire data set, and then use that as an initialization for the outcome-specific one just in the train set. And that still preserves all the nice properties, but it like massively increases the stability of the estimation. There's also no publicly available software, which is why, you know, I'm going to make some, right? Because that's important. Okay. How are we doing on time? Okay. Do you guys want to hear about text as confounder? How you feeling? Okay. Cool. All right. All right. So this comes from a paper with Molly Roberts and Rich Nielsen. Here's the backdrop. Here's the application. Censorship in China. There's a long history of repression of speech in China, and particularly that in the digital age is internet censorship. Gary talked about this a little bit. That project that he talked about, that was with Molly, who is, you know, also on this paper and is sort of the driving force behind this particular application. We know that the scale of internet censorship is pretty huge, hundreds of thousands of censors. And there's a lot of jailing of bloggers as well, on a much smaller scale, so like hundreds of people arrested. And this is sort of a scary proposition for, you know, the maintenance of free speech. So what we want to know is how people react to online repression. Gary and Molly's previous work with Jen Pan had been about sort of picking apart like what it was that is being censored, what was the logic of why it was being censored. We want to know now, how do people react to censorship? Lots of governments try to control online information, but the thing is that censoring the whole internet is like really, really hard, because it's always going to be that the number of bloggers is much greater than the number of censors. So it's a little like trying to empty the ocean with a bucket, right? Like it's just going to be very difficult. And when there is limited external enforcement, we might believe that self-policing becomes an extremely important part of the process. So for those who are familiar with Bentham's panopticon prison design, it's the idea that you know, there's a guard in this little tower here, and he could be watching you at any time, but you don't know. And so the argument that is made is that people then like behave themselves more because they could be being watched. And what we sort of want to know is that that is happening in the censorship case, right? Basically, are people self-censoring and doing some of the job of maintaining this repression for the regime? Okay, so it could be that the government is trying to scare people or encourage self-censorship by like signaling that certain topics are off limits. And this really could turn out in one of two ways, right? Bloggers could take the cues and self-censor, or they could like hate the censorship and rebel. And we don't really know which one is happening. But if we want to understand the mechanics of how censorship operates in the modern environment in China, then we need to understand the dynamics of this self-censorship behavior. But it's very, very difficult to measure for all the sort of common causal inference reasons. So one of the things that we recommend when we're doing causal inference is we say, think about the perfect experiment. And so here's the perfect experiment, illustrated with some nice pictures of the censorship police. So the first thing we would do is we would be the Chinese government. Then we would randomly assign censorship to different people. And then we would see what they write after being censored. This is pretty cool, but there's a couple problems. First, it's pretty unethical, as you guys probably know even before the ethics class. And we aren't the Chinese government. So we're going to need another approach, but it's fine because math is going to come to the rescue. Okay, so we're back to our fine-hatted friend. He's returning from this morning. We like him. He's very happy. And so here's the best approximation. We're going to find two bloggers that are similar users with similar histories of censorship and a similar number of posts. And they're going to write two very similar posts, except it's going to, on the same day, except it's going to turn out that one is censored and one isn't. Right? And we're going to use those as counterfactuals for each other. Okay? We think about this as like a censorship mistake, right? Basically, they both had sort of good probability of being censored, but it turns out only one did. And that's going to allow us to make a comparison that isn't, doesn't have the confounding problem. Yeah.
I'm just curious, in terms of in practice, how would you actually measure the similarity between two posts for that matching?
That's what the rest talks about. Yep. Okay. So does the censored blogger's behavior change? We can ask this question. We can ask if the censored blogger stays away from a particular topic, or do they pursue a particular topic. Like once we can make this comparison, we can measure all kinds of different outcomes. It's great. Okay. So we're going to use a procedure that we think of as text matching. And that is that we're going to take the idea of text as a pre-treatment confounder. So before it was the outcome and treatment, and now it's this pre-treatment confounder that's causing selection bias. And once you start thinking about text in this way, we found it was sort of a surprisingly frequent problem. It hadn't really occurred to us before we started talking about these applications, but then it shows up a lot. And so in the paper, we have a few applications. This one I'm using as a runner for this talk. But also, do the targeting of targeted killings of Islamic extremists create interest in their work? Basically, it's like, is there a martyrdom effect? And in international relations, are women cited less frequently than men? Now, I should say this third one is just like an empirical fact. Like, it is true. The question we really want to ask is something like, does the fact that the article is perceived as being written by a woman, like it has a woman's name on it, does that cause it to be cited less? Right? And so for those familiar with, there's a sort of question about like, what is manipulable in race and gender questions in particular, and this has come up a lot in economics. There's a similar thing going on here, and I can talk to you about it, but for now you can just think about it as like, what's the gender effect on citations? So the problem is that we can't just apply existing matching methods because they do very poorly on high-dimensional data. One way to think about this intuitively is you can't possibly match on every single word, and you wouldn't really want to. Like, you don't want to restrain yourself to a situation where the text is exactly the same. You're trying to find texts that are like largely about the same thing. And we care in particular about controlling for covariates that are going to be predictive of treatment, in this case, censorship. But with text, we don't necessarily know what predicts treatment, and so we're going to need some procedure that helps us work this out. So one thing when you present this to causal inference people is they say, well, why do we even want to do matching? Why not just do like weighting, or why not do insert this paper that I wrote 2 years ago? And I totally get that, and I think weighting is great. The reason we want to do matching is because we don't necessarily believe the balance metric that's implied here, right? We want to be able to manually evaluate the matched pairs. We want to know what the counterfactual is for our cases, because we don't believe that the model is perfectly able to capture things, everything about the text, right? If you think back to the principles I talked about this morning, we don't believe that there's like a perfect model for language, and so we want to be able to check that the model is picking up what we think it's picking up. And matching is very good for that because it explicitly says these two things are serving as counterfactuals for each other. And we can go in and look at them. And you'll see that, like, whereas typically in matching you want to try to evaluate balance across the treated and controlled groups, we're actually going to do that like manually. We're going to like show things to people and like have them evaluate pairs. And if they're matched together, they should really rate them as more similar than if they're not matched together. Okay. So what we're going to do is we're going to construct some analogs to current methods. An analog for propensity score matching and another for coarsened exact matching, which is what was on slides 1 to 25 of Gary's talk the other day. I was kind of hoping he was going to do it. It's going to save me a bit of time, but it's fine. We're going to identify some benefits and drawbacks of each, and then we're going to create a new method that sort of combines the best of both of these. We're also going to introduce some approaches to balance checking. And the simple idea that we're going to have is that we're going to match on a density estimate of the joint distribution of the covariates, emphasizing things that are predictive of the treatment. So we're basically going to get a density estimate of the text. We're going to match on that, but we're going to prioritize certain things that are, for example, in the example we're using, predictive of censorship. Okay. So in matching, the goal is to get to a space where conditional on the confounders, the treatment is independent of the potential outcomes. And there's a lot of ways of doing this. There's propensity score matching and coarsened exact matching, and much like the topic models, just so many things. So you can see I got tired much sooner on this one, but there's a lot of different methods. And we're going to just pick two of those. Propensity scores, which models the probability of treatment, and then essentially you find two things that were equally likely to be treated. And coarsened exact matching that basically says we're going to match on everything. Both of these strategies scale pretty poorly with high dimensional covariates, and so we're going to fix that in the process. Okay, because we're sort of running late, I'm just going to sort of skip through this little bit. Say we have a better way of estimating the propensity score, and it's fine. Let's skip a little bit through coarsened exact matching, except to say that the principle of coarsened exact matching is that you're going to take a variable and you're going to coarsen it, which basically means that you're going to take a set of values and sort of treat them equivalently. So say I take, your 9th, 10th, 11th, and 12th grade, and we're just going to call that like some high school, right? That's the idea. We're sort of coarsening into natural categories, and what we're going to do instead is we're going to coarsen across variables. So the previous approach coarsens within levels of a variable. We're going to coarsen across variables, which is we're going to say take a bunch of words like say tax, income, and tariff, and just sort of jointly call them economics. And we're going to do that basically with a topic model. That's like how that's going to work. Okay. So why does the propensity score strategy not work? Well, it's because that two things that are equally likely to be censored, have an equal propensity to treatment, aren't necessarily semantically similar. And that's not in itself a huge problem, but it makes our ability to validate the model extremely complicated. And so what you'll get is things like pornography, which we know that the regime censors, is really not equivalent to a protest, right? It would be very difficult for a sort of average user to say, oh, these two things are equally likely to be censored, because it's not quite clear what's going on. But when you do the topic matching, when you do the coarsening across topics, you have this problem that things about the same topic aren't necessarily equally likely to be censored either. And that's because a parade is not, is quite different than a protest. But they're both large gatherings of people and could easily have sort of overlapping words. And so we're going to need to capture both the propensity for the thing to be censored, but also this thing that sort of makes sure the topics are comparable. And so we're going to do that essentially by jointly estimating the probability of treatment and the topic density. And then we're going to match on the topic proportions and the topic-specific probability of treatment. So we're going to do this with the structural topic model, and we're going to use the content covariate. I'm going to just kind of leap over this part again, just because we're running a little late on time, and so just I cut that preemptively. See, I actually knew it was going to be long. Cool. Okay. All right. So let's say that we've done this matching. So now we need to assess balance. We need to know that we've gotten to a place where the treatment and the control groups look alike. And there's no single unified balance metric that we believe, and so we're going to have to use a few different ones. So we look at balance on words associated with treatment, like basically words that are in the original sample, highly likely to be censored, or highly unlikely to be censored. We want to see that that balance works out. We're going to show balance on estimated topics. So if we have a topic about economics, we want to see that's reasonably balanced across the data sets. And we're going to do something that all of these methods, the propensity score and the topically coarsened matching, are going to have this bag of words assumption, right? We're going to throw away word order. And so what we're going to do here is we're going to reintroduce word order in our balance checking. We're going to make sure that in the sort of matched sample, we have balance along a measure that actually respects the order of the words, and for that we're going to use something called a string kernel similarity. And basically what it's doing is it's measuring similarity in sequences of characters and words. And then we're finally going to do human comparisons. And this is obviously a lot easier to do for tweets than it is to do for novels, because you need to show people 2 documents and say how similar these are. And if you drop, you know, like Anna Karenina and say, like, how similar is this to War and Peace, that's going to take some time. And we have but so large a research budget. So, what's the answer? We've replicated this now in a much larger data set, but in this first one, 593 bloggers over 6 months, 150,000 posts. We returned to blogs afterwards to measure censorship, and we're finding censor mistakes. We're also going to match, in addition to the text, we're going to match on the date, so we need this to happen at the same time. We're going to match on previous censorship, and we're going to measure on previous sensitivity, which is basically how probable we think it was that it would be censored. And we want to know how treated bloggers react to censorship. The outcome is basically that for bloggers that were censored, the censorship rate, we're going to measure, the censorship rate after the sensitivity of the blog text and the topical content of the blogs. Okay, so in the original data, here's this measure that respects word order. This is like a distribution of string kernel similarity between random pairs of documents. You can see it's fairly low. When we do the propensity score matching, there's some that match really well, but you still get a bunch that don't match super well. When you do the topic matching, they become a lot more similar. And when you do the combination of the 2, the match pairs are like really similar to each other. Okay. So we end up using a fairly small set here, about 46 matched blogs. They're nearly perfect matches. You could loosen this up if you wanted to. Yeah.
So how much of the difference in similarity comes from just decreasing the number of matched blogs?
Oh, quite a lot. Yeah. And so what we're doing here is we're estimating essentially a feasible sample average treatment effect on the treated, which is basically the treatment effect on the treated for those where we can attain balance. Now you can loosen this up quite a bit, and in the paper, in the case about the Islamic extremists, we don't drop any treated units, and so that's a good case of where like we don't do that stuff. In this case, we felt more comfortable doing so. Okay, so most match posts are about the Boshilai incident or the Maoist protests, so this is going to be a thing where like this is the area where we can get this treatment effect. 5 posts after treatment, the treated group has a censorship rate of 20%, and the control group has a censorship rate of 7%. So seemingly, they continue to write more posts that are censored, right? This goes to the, like, it pisses them off thesis. We also estimate the text to be significantly more sensitive, and they talk, we observe, significantly more about the Boshilai incident after censorship than the control group. They also talk significantly more about CCP history and the Maoist protests. This is sort of what the match ends up looking like. This is the predicted censorship probability text of the post, and you can see sort of this is the point of the match, like the point where the one is censored and one is not, and the treatment sort of goes up into this more sensitive area. Okay. So limitations here. We use this piece really as a first step in framing the problem, thinking about text as a confounder and not necessarily as like a definitive solution, but certainly like a useful one. Right? I think there's lots of work to be done here, and this is like we're sort of coming into a fairly new space. When we started the work, there was actually almost nothing that used the selection on observables type setup, which is what we're doing here. In high dimensions, but it's actually becoming an increasingly crowded space. The thing is most of the work is centered around a sense where we believe firmly that we have the correct covariates, and we really care about balance along the covariates we observe. And in this context, we think of the text as sort of like weak proxies for the thing that is actually doing the confounding, and hence the need for sort of human evaluation of the matches. So correspondingly, our work places a greater emphasis on the human evaluation than the theoretical results. There's lots of potential applications. But the key thing here is that the text has to be pre-treatment, right? Because we're treating as confounders. As Gary said yesterday, don't condition on post-treatment things. The text has to be more confounder than instrument. In other words, so an instrument is something that affects the treatment but does not affect the outcome. If the text is primarily that, then what's going to end up happening is you're just going to like kill the power in your study here. You're basically like killing where all the information is coming from. So you need to like focus, and I can talk more about this point later. But so it needs to be something where that text is also going to affect the outcome as well as the treatment. And it has to be that, in a technical sense, the backdoor has to be blockable through the low-dimensional representation. In other words, the confounding has to be going through something that is low-dimensional. Otherwise, controlling for the low-dimensional thing does like not solve the problem. So overall, we talked about 3 very different roles for text as outcome, treatment, and confounder, and talked about new ways of thinking about the role of discovery in causal inference designs. Some new assumptions and trade-offs here, like the analyst to do SUPFA and the sufficiency conditions we talked about in text as treatment. And I think this is like a really exciting space for new work. I think the best work right now in causal inference is the machine learning causal inference hybrid. And I think the causal inference text hybrid could also be really, really productive. Yeah.
I think there's a 4th role that you guys haven't gotten to, and that's text as a source of heterogeneous treatment effects.
Yeah,
so
text as a moderator, yeah.
You must be familiar with, Athian n-bins and Athian wager. They're looking at heterogeneous treatment effects, learning conditional average treatment effects using these high-dimensional non-text data sources.
Yeah.
And it seems like the effect of a treatment on a firm where you have some kind of disclosures or their contracts or collective bargaining agreements, or the impacts on states where the constitution of the state or the legal apparatus running. I think text would provide a lot of interesting measures for heterogeneous treatment effect capturing those.
Yeah, I think that'd be really, really interesting, and in some ways, that would be a lot more straightforward than either of these. And a lot of Susan Athey's stuff is already heavily using the train test split idea, so this would just slot right in very nicely.
Why do you think of some of these as text-specific issues? It seems like the thing you brought up, particularly in text as outcomes and text as treatment, could be on any high-dimensional.
Yeah. No, it's basically these things are true for essentially any latent construct. So the answer is really it's a pragmatic concern about scoping. So when we had started, and the draft that of the matching paper that's still up online is actually very about high-dimensional data in general, for which generative models exist, which also includes genetics data and various things like that. And I think it's just, at the end of the day, it's it does have those applications, but it's overreaching to try to do all that at once. And so things whereas we're able to make an argument, particularly when we're talking about human validation, we can do that with text much more clearly. And so it allows us to kind of, I guess, leverage the things that are particular about text and language in our particular skill set. But you're totally right that there's nothing here that isn't also applicable sort of in all 3 cases to sort of any latent construct. This would be true with nominate scores and voting ideal points and very psychometric IRT things. All of this is true there too.
Should I turn off the live stream and then we can turn to Q&A, or did you have other stuff to cover?
Nope,
Okay.
that's it.
First, we can see that Gary King not only trains outstanding researchers, but also trains them endurance, because Brennan has been talking now for an hour and 45 minutes, and I think we'll all agree it was awesome. Thank you so much, Brandon.